Statics is the physics of objects that are in equilibrium, which seems kind of dull, but it's actually very important. Now, just as a reminder, a review, that word equilibrium means that the net force on an object is zero. So an object in equilibrium is at constant velocity or not moving at all. And most of the examples we're going to be looking at today is going to be where things are in equilibrium and they're not moving. The net force on them is zero. Okay, so the broad topics we're going to cover here, we're going to do a very, very quick review of free body diagrams and a quick review of what tension is, what kind of force that is, and how it appears. And then we're going to start using vector diagrams to solve problems in statics today. Okay, so let's start off. I promised a quick review of free body diagrams, and here it is. Remember, free body diagram, we represent the thing that we're interested in as just a dot, and then we represent the forces as arrows pointing away from that dot, and we label them. So, for example, if we had a weight hanging from a string or from a physics teacher's hand, the weight would be the dot. The force of gravity is the weight of the weight pointing straight down, and then straight up is the tension in my fingers holding it up. And in this case, the mass is in equilibrium. It's not accelerating, which means that the tension in my fingers is the same as the weight of the mass. We need to talk about tension too, and I'm going to show you kind of an odd one and maybe surprising one. So here's a diagram here, and I want you to think about this and answer this question. We have a spring scale here, which is suspended between two strings, and on each end of the string there is 100 Newton weight hanging. And the question is, what does the scale read? Does it read 100 newtons? Does it read 200 newtons? Or does it read 0 newtons? All right, so think about that for a moment. Pause it if you need more time, because I'm going to show you the answer right now. Here it is. Okay, the answer is that it reads 100 newtons. Okay, 100 newtons, which is a little surprising. Most students choose 200 newtons because there's 100 newtons hanging here and 100 newtons hanging there. But the actual answer is 100 newtons. And this kind of walks you through a little bit. So what we think about is, what does a scale read? If we had a spring scale hanging from the roof, and we hung 100 newtons on it, then the scale would read 100 newtons. And if we took that string that was suspending the whole system and we put it over a pulley and attached it to a wall, it would still read 100 newtons. I think we can all see that. Now, if we then moved the scale up so that it was in that horizontal string, it would still read 100 newtons. And then finally, we have to think about our third law a little bit. And if the block is pulling on the string with 100 newtons, that means that the string is pulling on the wall with a force of 100 newtons. Third law tells us that the wall is pulling on the string with a force of 100 newtons. And if instead of having a wall, we just attach another 100 Newton weight over here and hang it off a string, that 100 Newton weight provides the 100 newtons that holds this one up. And the scale will still read 100 newtons. See, it turns out that a spring scale like this, spring scale measures tension. It doesn't really measure weight. So this is a 500 gram mass, which has a weight of about 5 newtons. So when I hang it on here, the scale reads about 5 newtons. You'll have to take my word for it. Okay, so 5 newtons pulling down on this, but my finger has to be pulling up on it to keep the whole contraption from falling to the ground. So there is 5 newtons pulling up on the scale and 5 newtons pulling down on the scale. And the scale's not moving because it's in equilibrium. So that means the tension passing through the scale is 5 newtons. And the spring scale is actually reading that tension. It is not reading weight. The tension happens to be equal to the weight. The spring scale is measuring tension. I can also put 5 newtons of tension on it horizontally, and it still reads 5 newtons. Okay, it's about tension, it's not about weight. And that idea of an understanding of what tension is kind of helps some students as we go through these examples and concepts. Okay, so let's transfer this to free body diagrams again, okay? So this was the example of the horizontal scale that we just did. So this is a free body diagram of it. The dot represents the scale itself. We had 100 newtons pulling to the right and 100 newtons pulling to the left. Now, that's the free body diagram. Now we're also going to make a vector diagram to figure out what the net force is that's acting on the scale in this case. And we know intuitively that the net force is zero because it's in equilibrium. It's not accelerating. But what does that look like in a free body in a vector diagram? So I'm going to make a clone of this one here. There it is. Okay, there's one vector. That's the vector to the right. Now I'm going to make a clone of this vector. Remember, vectors are numbers that are represented by arrows, but they're still numbers. That means we can copy them and move them around the page, and they're still going to be the same value. Okay, so if I use my tail to head method or tip to tail method, I'm kind of arbitrarily using this as my starting point, and we have a force going this direction and another force vector coming back, and we lay it tip to tail to add them together. And we see that it comes back to the same point, which means, and the vector, the resulting vector of all these forces is from the original origin to the final tip of the tail. That's the net force. And in this case, the net force is zero. So yeah, F net is zero. This one is in equilibrium, and we can see that in the force diagram. Okay, well, what if we have a tug of war? So in this case, and one team is winning here. So we have a force to the left of some force, and we have a larger force to the right. So the team to our right here is winning, and this whole thing is going to start accelerating to our right because we can tell intuitively these guys are winning. It's all going to start going that way. So let's do the same thing. We're going to make a vector diagram out of this, force vector diagram out of it. We're going to clone this one, leave it there. So this is kind of our origin. Now we're going to clone this one. And we're going to do tip to tail method. We're going to lay it on the right there. So we have the tail of the second vector laid on the tip of the first. And that gives us a net force. Let's do this. The net force is from the original starting point to the final ending point. So the net force in this case is not zero. The net force is to the right. And that is the length of that force vector. So in this tug of war, this is not an equilibrium situation. Okay, so now let's consider another situation. So in this case, let's imagine that we have three kids who are fighting over a frisbee, and they all want the frisbee. So we have one kid pulling this direction with a force of 100 newtons, and we have another kid pulling this direction with a force of 100 newtons. I'm going to try to make that the same length. And then the third kid is pulling this direction with a force of 100 newtons. Okay, so they're all equal strength. They're all pulling rather in opposite directions because they want the frisbee. Now, our common sense, intuitively, we say if we have equal forces and they're evenly spaced around the circle here, pushing in three directions, the frisbee's not going anywhere. This is going to be a complete tie for a moment. Okay. Because as I say, we have, it's a symmetrical situation, and I'm hoping that your common sense will tell you, yeah, that the frisbee's not going anywhere. So the net force on the frisbee equals zero in this case. Now, how does this look in a vector diagram? We're going to call this one number one, this one number two, and this one number three. And what we can do is we can copy these three vectors, make a force diagram to figure out what the net force is. Now, we already know intuitively that the net force is zero, but what does that look like when we transfer these force vectors? Okay, so we're going to start with the first one here, the one with the single tick mark in it. We're going to say that that is our frisbee, and we're going to copy this one as best we can. 100 newtons. Then we are going to go with the second one here, which is going to go out in this direction, also 100 newtons. That's the second one. That was the first one. And then we're going to take the third one, comes down here. That's the third one, also 100 newtons. And as you can see, when we put these three vectors together using the tip to tail method, it makes a closed triangle. Because we wound up where we began with our force vectors, that means that the net force equals zero. Okay. Now, suppose just for a moment that two of these kids decided to work together, okay? So that's going to change it. So now we have two kids pulling like this, and the third kid pulling like this. Now the frisbee is going to start going this way. We can tell intuitively that the net force is going to be something going up in that direction. We're still going to say that it's 100 newtons for each. And in this case, the force diagram is going to look something like this. This is where we start. It doesn't matter what order we put these vectors in, but we're just going to do the first one here. It's going to look something like this. That's the first one. Then we're going to do the second one. It's going to go something like this. That's the second one. And then the third one comes back, and it doesn't make it all the way back. So that's the third one. So in this case, the net force is from the origin to the final tip. So this right here, that's the net force. So if the three vectors do not come back to the origin, that means that there is a net force. And in this situation, the frisbee is in equilibrium. It's not accelerating, it's not going anywhere because the force vectors return to their origin and the net force is zero. And in this case, where we have two kids pulling in, helping each other, pulling in kind of the same direction, now there is a net force, and this one is not in equilibrium. It's going to be accelerating that direction. Okay, now the problems that we're doing today in your homework are all equilibrium problems. And this means that we can make force diagrams where of the forces involved in the problem, where it will make a closed triangle or a closed shape. Triangles for the ones that we're doing here, okay? And this is a very powerful method, which is not mentioned in the book very much, okay? But making force diagrams where the net force is zero, we know it's going to make a closed triangle, and then we can use our trigonometry skills to analyze that triangle and figure out answers to these questions. Okay, so let's do some examples here. We're going to start off with a simple one. All right. So these hash things, these are solid walls, and we have two cables attached to the wall to some object here, like a ring of very low mass. And then we're going to pull on it at this angle with a force of 400 newtons. And this angle here is 50 degrees below the horizontal in the diagram, excuse me. And what we want to figure out is the tension that is in rope number 1 and the tension that is in rope number 2. Okay, so this one we don't even need triangles for. We can use triangles for it if we want to, but we can just go figure out just the components of the force of this this force vector. Okay, so we have 400 newtons. This is 400 newtons. And there is a horizontal component to that force, and there is a vertical component to that force. And this is 50 degrees because that was given. So now we use that, says in newtons, okay? So now we can just use our SOHCAHTOA to figure out these two components. This is just like we were doing with the weights on the slope before. Mathematically, it's the same. So 400 sine 50 degrees equals something, and 400 cosine 50 degrees equals something. All right, so 50 sine times 400, that's in the glare, that's better, equals 306 newtons. 50 cosine times 400 equals 257 newtons. Okay, so the short side is going to be the 257. The long side is going to be the 306. When we transfer that to this diagram here, we are pulling more down than we are pulling to the side because this is 50 degrees. This is more than 45 degrees. So the force is more downward than it is sideways. So the greater force is going to be up here. That's going to be the 306 newtons. And the lesser force is going to be here, 257 newtons.